Current methods for test time scaling in AI rely on a fixed architecture. Systems generate thousands of search prompts, but the underlying language model remains frozen in place. Its neural weights cannot change, setting a hard mathematical limit on its capacity for novel discovery. To break past this limit, a method called TTT-Discover executes reinforcement learning directly on the test instance itself. We stop prompting a frozen model and instead allow the network's weights to physically adapt in real time as it attempts to solve the specific problem in front of it. This animated diagram shows how we structure scientific discovery as a reinforcement learning environment. The problem description defines the parameters. We start with a candidate solution, defined as the state. The language model then generates an action, a piece of code designed to improve that solution. The environment parses and executes that code. This transition function yields a continuous reward based on the code's performance. If the reward crosses the highest previously recorded threshold, the model establishes a new state-of-the-art. Breakthroughs depend on an AI adapting its internal logic to a specific environment that exists entirely outside its training data. Standard reinforcement learning algorithms, such as PPO and GRPO, are built for a specific goal: deployment robustness. Deployment robustness is the mathematical pursuit of the highest average expected reward. A standard algorithm optimizes the model to perform reliably across all possible actions it might take. This scatterplot illustrates the core conflict in test time scaling. Standard RL optimizes for the safely clustered data points in the center. Scientific discovery ignores average performance entirely, requiring only a single maximum outlier to establish a new state-of-the-art. Standard algorithms actively suppress the high-risk actions needed to find that outlier. If a pathway fails 99 times but produces one breakthrough, the high failure rate drags down the mean expected reward, and the standard algorithm learns to avoid it. To build an effective discovery engine, we must rewrite the learning objective and search heuristic to ignore the average, hunting exclusively for extreme statistical outliers. A standard policy gradient update pulls the central marker toward a large, shallow valley of safe, low-reward outputs. It bypasses the narrow, deep peak of maximum reward. The model ignores the state-of-the-art solution, treating that single extreme success as an anomaly to be smoothed out. TTT-Discover solves this structural blindness by replacing the standard update with the entropic objective. The entropic objective introduces a tilted distribution. Instead of averaging the batch, an exponential tilt violently warps the distribution, assigning massive weight to the highest scoring data point. This forces the gradient update to prioritize the exact pathway that achieved the maximum reward, ignoring surrounding failures. The entropic objective strips away the model's ability to learn from safe, average successes, forcing it to learn exclusively from its most brilliant, risky mistakes. Targeting the maximum reward is unstable. Without a restraint mechanism, gradient updates overfit to a single lucky rollout, destroying the model's general reasoning capabilities. TTT-Discover prevents this by implementing an adaptive beta parameter, which acts as a dynamic braking system for the gradient update. This visual equilibrium scale illustrates the KL divergence constraint. It balances the heavily tilted spike of the new rollout against a fixed constant, ensuring the update does not deviate too far from the original batch density. To find the exact balance point, a bisection search calculates the optimal beta value based on the batch's shape. Sudden outliers trigger a small beta value to prevent collapse, while flat batches trigger a large beta value, pushing the model harder. This dynamic constraint allows the system to relentlessly pursue extreme outliers without destroying the underlying neural representations required to generate valid code. Generating complex algorithms requires long, effective horizons. If a model starts from scratch on every attempt, it cannot reach deep solutions. It must maintain a buffer and warm start from its previous best states. This branching decision tree visualizes the state reuse architecture. The standard baseline is the AlphaZero PUCT algorithm, which evaluates paths based on the mean reward of the connected branches. By averaging the success of all children, it heavily penalizes risky branches. If a state produces a 99% failure rate, the average pulls the score down. The search tree abandons the path, ignoring the single massive success attached to it. TTT-Discover replaces the mean calculation entirely. The node value tracks only the absolute maximum child reward. Under this rule, a high failure rate is irrelevant. A single massive success violently recalculates the tree, sending a wave up the lineage, while failed branches fall away. To prevent overexploiting a single dead end, a rank-based prior and modified visitation penalty ensure the model continues testing unvisited nodes in the archive. Rather than seeking a reliable neighborhood of solutions, this search tree acts as a targeting system, locking on to the deepest, highest reward solution in the space. We could observe this architecture at work in Erdős's minimum overlap problem, a complex challenge in additive combinatorics regarding the limits of step functions. This line graph displays the previous state-of-the-art upper bound, achieved by Google's AlphaEvolve system. The model hit a mathematical limit at a symmetrical 95p step function. TTT-Discover improved upon that bound by generating a vastly more complex, irregular, asymmetric 600p step function. To map this result, the generated algorithm had to navigate strict mathematical constraints, optimizing bounded limits and exact integrals while utilizing simulated annealing to refine the shape. The system succeeded because the entropic objective allowed it to internalize an extreme, irregular outlier that standard optimization algorithms would have smoothed out of existence. We see the exact same dynamic in GPU kernel engineering. In the GPU mode tri-mole competition, the objective is to minimize the runtime of matrix multiplication kernels. This chart tracks kernel runtime across training steps. Naive reinforcement learning and modified search heuristics fail to beat the best human submissions. However, combining the entropic objective with max reward search causes runtime to plummet, breaking the human threshold to hit 1203 microseconds. This new performance record was achieved using an open-source 120 billion parameter model, executing the test time training loop for only a few $100s of compute. True test time scaling temporarily forces a language model to physically rearrange its internal weights to perfectly fit the specific parameters of a single problem. Scientific discovery depends on engineering models that can teach themselves the exact math required at the moment of testing.